my name's Ben. I'm an electrical engineering major and I'm the team lead.
Hi, my name is Ali Al-Bakr. I am an industrial engineer and I am the procurement leader in this team.
Hello, my name is Lewis Brownlee and I'm majoring in computer engineering.
Hi, my name is Jialiang Li. I'm engineering management major.
Hi, my name is Hassan Ligraini and I'm a mechanical engineer.
Hi guys, welcome to Team 22058's Design Day video presentation. These days, COVID is spreading around like crazy. And the best way to prevent it is to get that fresh, good air quality inside your home. That's why we partnered with Nature's Cooling Solutions to bring you the world's first smart air ventilation fan. Let me show you around the unit. So right here, we have the whole box, which will fit inside your window, bringing you cool, fresh air when you want it, and closing dampers to make sure it doesn't come in when you don't. Our team worked hard to create the electrical components inside, including the display, the stepper motors to control those dampers, the buttons to control the unit, a Wi-Fi connection so you're always up to date with what's going on with the air quality in your home, and of course a fan to bring all of that good, cool air in. We'll bring you through each component, showing you how we did it, why we did it, and how it works. Let's get going.
To use ESP32 for our project to run the whole system. This microchip was designed specifically for Wi-Fi connection. It has enough pins, RAM and flash to run everything. The chip itself cost $1.80, but the whole board cost $10. So it's pretty much affordable for our project.
Hi, our mechanical development in this project was like to find a solution to get like a display fit with the buttons in the system. This mechanical side was developed by the SolidWorks. We have been tried like many different shapes for that, and we come up with this one because it's easy like to click in, if you can see it here, for the buttons to control the fan. And there's something with the like hook to the system with the front housing, and this is the best design that we can.
So for our display, we decided on a 2.8-inch SPI driven display. This has a few benefits, but the most being the amount of saved pins we'll have. Because SPI only uses 4 pins, we don't have to worry about having a traditional 8 like you would on a parallel display, or 16 like you would on an HDMI display.
All right, one of the major features of this project is to make sure the fan can connect to the internet to be able to control with a fan or with an app, and also optionally be able to communicate with an aware air quality sensor. So here we have the aware element, it's an air quality sensor, so we're going to connect this fan to the Wi-Fi to be able to be controlled with an app, and then it's going to pull data from this as well. So if we pull up the Wi-Fi connection screen, it'll say we're not connected to Wi-Fi. If we press the plus minus, it'll start the Wi-Fi connection process. So now in the app, we are going to broadcast the Wi-Fi information to here, so that it'll be able to connect to Wi-Fi. And on the app, we receive a success screen. We will receive a success screen here in a minute too. We can go back to the temperature, humidity, but now there's a third menu, which is the aware air quality. So now this is pulling data from here, and if this ever updates, you will see it on here as well. In addition, on the fan, it will connect and it will show all the data from here. and we can change our goal. For example, maybe we want to set our air quality goal to 90 instead of 85. We can update it, and it will now show 90 on here. And in a similar way, we can update the temperature and the humidity and all other aspects as well.
I'm gonna start recording now. Probably gonna be the first of many trials. Let's dig into the software design a little bit. Here we have the software diagram that essentially just explains the different software components for the fan, the app, and as well as the external components. All the blue components in the middle are for the fan. We have the free RTOS within the ExpressIFs software development kit that manages everything. And within that we have ESP touch thread, an MQTT thread, an HTTP client thread, and everything else. We're not going to go into detail on this, but this is just a high level of kind of what's going on with the software. Just for fun, we'll dig a little bit into the software itself. Just the main function. This is the main function that gets called at the beginning. We call init, which I'll go to in a minute. Then we try to connect to the Wi-Fi from what's displayed, from what's stored in the board. And if this fails, then that's okay, but if it succeeds, then cool, we're connected to Wi-Fi. And if it does not succeed, well, the user can just start the Wi-Fi connection process manually. Here up here in the init function, we initialize all the different components, like the software components that I was showing you earlier, and then we start the sensors to get those up and running, and we start the display as well. So this is kind of behind the scenes of what's going on with the code. One last thing we'll show you is the device shadow on the AWS server. This is what's being stored in the server for the device. It shows the state of the device, the desired state, which the app reports. You know, we want the temperature number to be 69. We want the fan speed to be set to 1, for example.
Attached to the fan output on the ESP32 board is a triple transistor setup with a emitter of each set into the base of the next. This allows for some extreme current multiplication so that whenever you want the fan on, it turns on.
Because it was very important for our sponsor to use low-cost product, we managed to find affordable and readily available products to use. The total cost, as you can see, for the part was approximately around $55.
Thank you for your watching our video. We are excited to see you on Design Day.